And today I am a speaker. So let me share my screen. Here is my screen, and here is my talk. The talk is named Universal Generalized Functional, and this is a joint work with Naoufel Salhi from Tunisia. This book is dedicated to the memory of such a very nice mathematician, a very kind person, Habib Kurdian, who died a year ago in Sweden. He was a long time head of the Department of Mathematics in Tunis El Manar University, and spent a lot of efforts to bring to grow up probability community in Tunisia. And I remember the time when I visited him several times, and I remember the time when Habib invited me to his office. He used to smoke a lot, so imagine instead of pointer cigarette in his hand. And we discussed something about white noise. He was fan of this theory. And at those time, I thought that I have something new in my mind. So when we with Naoufel were asked to write a paper devoted to the memory of Habib. Finally, I get an idea of this talk. Let me present this idea to you. So let's start from the notion and understanding how useful are generalized functional for Wiener process. Let's start from the most widely distributed and most widely known generalized functional related to again most widely known generalized function or Schwarz distribution called delta function. This is nothing else than the measure of the unit weight concentrated in some point of Euclidean space. It occurs to be very useful in studying of linear partial differential equations, and then in a lot of branches of mathematics. The usefulness of delta function in probability comes from very simple formula. You see, if we consider random variable eta or random vector eta, which has continuous density, then one can expect that the expectation of delta function from eta, we don't know what is this, but at least we know what is the expectation. This is pairing of delta function with its density, and it must be a value of the density at the point x. So let us use such simple non-formal arguments. By the way, this formula can be formalized in a usual way. If we use, for example, family P epsilon, which is approximating sequence for delta function, it can be density of Gaussian distribution with zero mean and variance epsilon. Then one can at least say that the expectation of delta function from our vector must be some limit of pi epsilon, expectation of p epsilon from eta, and get the same result. Now let us see how useful are such calculations. And maybe one of classical and most known examples is Katz's formula for moments of the local time for Wiener process. Let Wt be a one-dimensional Wiener process. Local time of W usually is defined as the L2 limit L2 limit of such approximating sequence. This is integral from 0 to 1 p epsilon from Wt minus x dt. This is the local time at the point x, and naturally it is denoted for integral 0, 1 delta x from Wt dt. Then, since for every function phi on R we have such a nice relation, I mean every, I mean, for example, let it be continuous and bounded. So we have such convolution in the sense of usual Schwarz distribution. Then we can substitute this convolution inside of the integral. You see, integral from 0 to 1 f from Wt must be equal. The integral from 0 to 1 f convolution with delta function from Wt must be equal. Here I just write the definition of convolution in the integral inside. Integral with respect to r f of u delta 0 Wt minus u. This is a convolution. And then let's change the order of integration. Suppose we can do this formally. Then what we get? We get the integral from r f of u, and in brackets we have a local times at the point u. So finally we get the well-known occupation formula for local times. The integral from 0 to 1 f Wt dt must be equal to the integral from r f of u local time at the point u du. This is well-known occupation formula. Now let's consider, for example, moments of the local time at the point 0. It is, at least formally, again, this is the expectation of the integral from 0 to 1 delta 0 Wt dt in m power. Then let us write this m power as a multiple integral. Here, under integral, we have a product of delta functions from different values of w. But let me say that even from the rigorous point of view, it's okay, because if we have t1 not equal to t2 and so on, then we have a product of delta functions on from different coordinates in Euclidean space applied to joint density, and it's okay in a sense of Schwarz distribution. So we can continue and write this as a m factorial integrals over simplex, then use Markov property of Wiener process and take expectation subsequently and get such a nice formula. Here you see the nothing else than the product of one-dimensional normal densities with such variances at with the value at 0. So we will have finally square root of 2 pi in power minus m multiplied on the multiple integral with square roots, which can be precisely calculated with beta functions, but this is not my aim today. But Katz did this. So we have such a nice application, for example, of formal calculation with delta function from Wiener process. If one look for Rice formula, for example, for expectation of number of upcrossings of by the smooth centered process of some level, then again we can use delta function at least to get the guess what can be answered. It is very easy. So you see that calculations with delta function is from some process is very useful. Moreover, one can consider generalized intersection local time for Wiener process in RD. Suppose that D is less than 4 and U belong to RD and not equal to 0. Then such the quantity like double integral from 0 to 1, 0 to t delta u double wt2 minus wt1 dt d2 does not exist as L2 limit. But one can check that it can be viewed as a generalized functional from W in different senses. One is the following. One can consider Ito-Wiener decomposition of approximating family. So if Gn be a projection onto subspace of integrals of from W of multiplicity n, then for all Ito q's, then for all n which is greater or equals than 0, there exists L2 limit of such quantity. So at least we have some candidates for chaotic expansion of the limited self-intersection local time. And the kernels of this chaotic members of chaotic expansion can be calculated explicitly. Then formally, one can say that we still have Ito-Wiener expansion for such expression like self-intersection local time for Wiener process in multiple dimensional Euclid space. Of course, this series doesn't. But still, some information can be taken from here. Why? Because there is another view onto generalized functional from a Wiener process. So it's not only formal series, but in this case, if we take sufficiently many times differentiable random variable alpha, what does it mean for us? I will not recall the definition because this is not necessary now for understanding. At least you can recall that the Ito-Wiener series of such stochastically differentiable several times random variable alpha converge fastly than for usual random. Then one can organize the pairing between this formal generalized self-intersection local time and this variable just as it can be for usual two random variables having Ito-Wiener expansion. So we just have such a series and the series converge. It means that we have something like Schwarz distribution on the Wiener space. But let me emphasize, this is very important for future our consideration today, that this things heavily depend on the Wiener measure. So let me repeat, on the Wiener measure, we get something which can be paired with good functions, with smooth functions, like stochastically differentiable several times. Moreover, it has some sign. This expectation remain to be non-negative for non-negative alpha. So if we take our random variable alpha sufficiently many times differentiate and non-negative, then this pairing is also non-negative. It can be proved, but you can imagine the argument. It is not hard to understand because instead of this delta, you put p epsilon, our approximating sequence. It is non-negative, so maybe we can play with limits and prove that the final answer also will be non-negative. So we have non-negative functional, generalized functional on the Wiener space. And it occurs that there exists the finite measure nu on C01RD. It can be singular to Wiener measure. This is our case, by the way. In case of self-intersection, it is singular to initial Wiener measure, but it must be concentrated on the set of positive Gaussian capacity. Capacity is some characterization of the set in the space equipped with Gaussian measure, but if we have R3 and standard Gaussian distribution, capacity coincides with Newtonian capacity, at least for some parameters. So there exists such measure nu that for smooth random variables, this integral is nothing else than integral over C01 RD of alpha with respect to this measure nu. But this is non-trivial result which was proved by Hiroshi Sugita in end of I think in end of 80s of previous century. And let me note that this is not so how to say not so easy for understanding formula. Why? Let me recall you that we are discussing a random variable alpha, which has sufficiently many stochastic derivatives as a functional from Wiener process. Then let me recall you that alpha can be linear functional. Then it has sufficiently, it has infinitely many derivatives because all its derivative after one equals to 0. But also let me recall you that we can consider not only linear continuous functional, but linear measured functional. In infinitely dimensional space, we have a special kind of linear functionals relatively to measure, which we with which we equip this infinite dimensional space. So, relatively to Wiener measure in C01 RD, there exists a large family of measured linear functionals, which are simply L2 limits of usual continuous linear functionals. Why I am talking so long about these functionals? Because they are not continuous. They are not continuous at all. They are only measured functions from the first look of view. So you can ask me, if we have just measured function, which it is Borel function, so maybe it's defined up to the set of probabilities of measure Wiener measure 0, but nu is singular to this measure. So what we can do? How this integral is defined? But occurs that the random variables, which are sufficiently many times differentiable, are in some sense continuous on the set of positive capacity. So this integral is properly defined. But its definition depends on the Wiener measure. So we have such a nice representation. And this representation gives us the general procedure how to create a positive generalized Wiener functional. So let us consider on the space C01RD the family phi epsilon of smooth non-negative function, and then try to organize the limit phi epsilon from W. In which sense? In a sense of separate summands of Ito-Wiener decomposition, and we hope that this limit can be interpreted not only as a formal Ito-Wiener series, but we expect that it can be corresponding to some measure on C01 RD. Let me recall you that this measure can be singular to initial Wiener measure. So this is the procedure. We start from some smooth family, which is well defined for arbitrary element from C01 RD, and trying to get the limit in sense of Ito-Wiener decomposition and interpret this limit as a certain measure on C01 RD. By the way, we with Naoufel did this for self-intersection local time, which I mentioned as an example. And even I think that in spring semester, Naoufel made a talk about large deviation for those measures. So those measures became to a singular to Wiener measure, but still can be investigated, even we succeed to establish large deviations for it, in principle. Now, the main question of the talk. For which families of good function on real separable Banach space, there exists a wide set of probability measures G on this space. That family has a limit as a new measure or in a sense of chaotic expansion. So we are looking for families phi epsilon, such that for such family, there exists not only one measure on Banach space for which we can construct all previous subjects, but we are looking for the family such that for wide family of measures, we will have some limits. And it is natural to ask, for example. So, for example, phi epsilon converges to generalized function not only for Wiener measure, but for other probability distribution on C01 RD. Let me again recall you that the answer heavily depends on the measure which we consider. So we will see in example. Example. Consider C01. This is one-dimensional continuous function. Again, let's consider phi epsilon, which approximate delta function from the value of the function from C01 at the point 1. Then, for Wiener measure, this phi epsilon converge to delta 0 from W1. Here you see the formal Ito-Wiener expansion, and this delta 0 from W1 became to be generalized functional. It is, if I remember exactly, the member of space negatively differentiated function of order 1, minus 1. And corresponding, of course, it is non-negative. Corresponding measure on C01 is just Brownian bridge multiplied on 1 over square root of 2 pi. So we see that now we have a good construction. We have a formal series. We have a final measure. But let us apply the same family. Let me recall you. This is a family. Let us apply the same family to another Gaussian process. This is very simple Gaussian process, just eta t equal t multiply on some standard Gaussian variable. Yeah. Then again, this eta is a Gaussian measure. For functionals from this, for functional from L2 on this measure, we have chaotic expansion. We have all tools which we mentioned. So one can consider delta 0 from eta 1. It is evidently equal delta 0 from psi. And here you see its chaotic expansion. It does not contain now any integrals. It's just a sum of Hermite polynomials normalized by square 1 over n factorial. Here I discuss the Hermite polynomials of such kind. They are orthogonal with respect to standard Gaussian distribution and has leading coefficient equal to 1. Again, this is a formal expansion, of course. And it can be created in the sense of generalized functionals, but from this random process eta. And corresponding measure is definitely different. This is just measure in C01, which has total weight 1 over 2 pi and concentrated on the function totally equal to 0. So you see how large is difference. We have the same family, but we take another measure. And for this measure, we get another answer. The answer is the measure concentrated on one function. Besides, in the previous case, we have the distribution of Brownian bridge. These two examples shows us that when we discuss universality of the family, we have to take into account that the answer must be very different for different measures which we take on our Banach space. And it occurs that to characterize universality of the families, some additional notions can be used. These additional notions were introduced by me in the paper in 2000, devoted to some University of Anatoly Vladimir Skorokhod. And this is a notion of finite absolute continuity and polynomially non-degenerate measure. Let me recall you what is it. So let B capital be a real separable Banach space, and mu is a probability distribution. Suppose that for all linear functionals, continuous linear functional B, we have all moments. So in this case, people say that mu has all weak moments. Also suppose that the set of all finite dimensional polynomials on B is dense in L2 mu. I always suppose that we are considering probability measures on the Born sigma fields out space. There are a lot of conditions which are sufficient for density of polynomials in L2 B by mu, and one of the most known belongs to Skorokhod, and is that the characteristic functional of the measure is analytic in some neighborhood of 0. In this case, one can say that L2 B beta mu has chaotic expansion. What is it? Chaotic expansion organized as a orthogonal sum of K, where Kn is a completion of orthogonal complement of Pn to Pn minus 1. Pn is a set of polynomials of degree non greater than n. Okay, so for example, when mu is a Wiener measure on C01, then Kn consists from exactly the multiple Wiener integrals with respect to Wiener process of multiplicity n. But the structure of Kn can be very, very different. We will say something about this later. Suppose also that linear span of support mu is dense in B. So we have that. This is very simple condition which is necessary to say that our measure mu does not kill any non-trivial linear function, continuous linear. Now suppose that H2 H calligraphic 2 is equal to closure of the space of the continuous linear functional in L2 B mil. By the way, in Gaussian case, this is this H calligraphic indexed by 2 is exactly the space of all measurable linear functions. And also, by the way, in order to feel how ugly are measurable linear functional, let me tell you that if one consider a graph of measurable linear functional, then it is dense in the product B multiplied over R. It is dense. It is not some surface. It is dense in the product B multiplied over on R. And now let's define the subset of B, which consists of such integrals. Here you see some complexity related to the fact that under the sign of integral we have Banach-valued function. But this integral can be treated in the sense of Petit's, which means that we just take a new continuous linear functional from this integral, put it inside, get the answer, and this answer is again action of this continuous functional on some element of B. Now everything is well defined in Petit's sense. And we get a very interesting subspace of B. For example, it is compactly embedded in B. And it can be checked, it was proved by me in 2000, that H2 contain all admissible shifts and the direction of continuity for mu. Here we have no any assumptions that mu is Gaussian. So it is true for any probability measure. Now let us proceed with definition. The measure mu is polynomially non-degenerated if this nth summand from chaotic expansion can be put into continuous correspondence with the tensor product H2 in power n, where H2 is equipped with the Hilbert structure very easy. Yes, for two Petit's integrals, we have such definition of its product. This is exactly what we did for Gaussian measure, and here we are and here this requirement means that we can characterize the orthogonal polynomials with respect to our measure mu using Hilbert-Schmidt forms on this new Hilbert space H2. By the way, there are a lot of probability distributions which are polynomially degenerate. But of course, we have examples of good situations. So any Gaussian measure, of course, is polynomial non-degenerate. And Gaussian measure restricted on a set of positive measures. It occurs that it is already will be polynomial non-degenerate. I proved this statement not for any set, but for both in the initial space. And Vladimir Bogachev with his PhD student were succeed to prove the same, but for any set of positive measures. By the way, it is not necessary for measure to be Gaussian or even to be logarithmically differentiable, to have smooth finite dimensional distribution, to have such property. Some infinite dimensional discrete measures like distribution of such series. Here you see the series. where En is orthonormal basis in Hilbert space. Lambda n are positive numbers which decrease sufficiently fast, like faster than 1 over n logarithm n. And epsilon n are Bernoulli numbers. That's all. Then, of course, this is a discrete measure. The distribution of this sum is discrete, but it occurs that it is polynomial non-degenerate. Why we are looking for polynomial non-degenerated measure? One reason is containing exactly in the definition. For polynomially non-degenerated measure, we can easily describe orthogonal polynomials. At least one can say, oh, okay, let's take orthogonal polynomial of degree n corresponding to this tensor, to this element of tensor product. And such element will exist, and this correspondence is continuous in both sides, in both directions. But also there is another reason which I told you in the future. For polynomial non-degenerated measure, the chaotic decomposition of any random variable from L2 or function from L2 b mu can be associated with the unique sequence of the kernels. This is exactly what I say. Remark, this is another new reason. Notice that for polynomial non-degenerate measures, the inclusion H2 into LP for P is greater than 2 is continuous. This is very important. You remember, let's recall Gaussian variables which are centered. You remember that if psi is Gaussian variable with variance sigma square, then the expectation of psi in power 2n is equal to 2n minus 1 double factorial multiplies sigma to n. And this constant, 2n minus 1 double factorial, is universal. It does not depend on the concrete value of sigma. The same happens there. So it does not depend on the measure of function on which you take. Its LP moment, it exists. Its LP moment can be bounded by, of course, p 2p power of p power of its second moment with the universal constant. This is another very helpful property of polynomial non-degenerate measure. Now, consider another necessary notion for us. This is the notion of finite absolute continuity. It was also introduced by me in the same paper. So I say the measure nu is finitely absolutely continuous with respect to mu if for any n there exists constancy n such that for all f which belongs to a set of finite dimensional polynomials, degree not greater than n, we have the absolute value of the integral. It is well defined because we have continuous function, so we don't need any requirement. The integral is less, absolute value of this integral is less than or equal than constant, and the L2 norm of this polynomial with respect to measure mu. Let me tell you that if we can say that this constant Cn does not depend on n, so if we for a moment arise index n here, then it occurs that this condition leads to existence of density of measure nu with respect to measure mu, and this density must be even square integrable. But in case when Cn is fixed only for fixed n, so it can grow up, we cannot say that nu is absolutely continuous with respect to mu. We will see examples. Notation will be following. We keep the notation of the absolute continuity, but add symbol 0, which means finitely absolute continuous. Let's consider some examples. The first example shows that the notion of finite absolutely continuity is purely infinitely dimensional. It is it has no big sense in finite dimensional case. In finite dimensional case, any measure is finitely absolutely continuous with respect to and arbitrary mu. Why it happened? It happened because the dimension of Pn, dimension of the space of polynomials, degree non greater than n is finite. So any norm there is all norms there are equivalent. So this is the reason why in a finite dimensional space it is no sense to speak about finite absolute continuity. But in infinite dimensional case, the situation is opposite. This notion became to have sense. It occurs that not every measure is finite absolutely continuous. The measure can be finitely absolutely continuous, but singular, and so on. So let me give you some examples. For Banach space C01 and Wiener measure mu, the measures corresponding to above-mentioned positive generalized functionals are finitely absolutely continuous with respect to mu. One can check it easily because they have chaotic expansion. It's enough. If the measure has chaotic expansion, then it is finitely absolutely continuous. So local time, self-intersection, Brownian bridge distribution, etc. And let me recall you that all these measures are singular to the initial Wiener measure. So we see example that some singular measures can be finitely absolutely continuous, but not all. Here is another example which shows us that not all measures are finitely absolutely continuous. For example, let mu be a Gaussian measure in L2 with zero mean and covariance operator which is diagonal with lambdas, and we know that lambdas must converge. The series from lambdas must converge. Then consider nu having weight 1 concentrated in one point H. We just take arbitrary vector from L2 small. If nu is absolutely finitely absolutely continuous, then for some C2 we must have the absolute value of scalar product phi h. This is, by the way, integral over mu of the linear functional phi must be less than C2, and here what we have. This is exactly integral over mu of the square of this linear function. So we have such inequality. In coordinates in the left-hand side, this inequality looks like absolute value of the sum h n phi n must be less than C2 and the sum of square of such squares. Now let's apply resonance theorem, and we get that H must be of such property. But everybody can produce H such that it belongs to L2 small, but don't satisfy this relation. So this relation is not always true. And from this point of view, we have an example which shows us that the measure which is very singular to initial measure can be not finitely absolutely continuous. Let me recall you that if nu is Absolutely continuous, finitely absolutely continuous with respect to mu, and mu is polynomially non-degenerate, then mu has a formal chaotic expansion like this one, and kernels of this chaotic expansion are element of corresponding tensor powers. So now the main idea, to guarantee that the family phi epsilon has a limit when epsilon tends to 0, and this limit is a positive generalized function, functional with respect to mu, let us ask for uniform condition of finite absolute continuity, namely, for any n there exists n such that sup of epsilon greater than 0 of such integrals is less than Cn, and here we have integral over b f square mu dx. So what is the difference between the usual finite absolute continuity? The difference is only that we require the same constant for any member of our family, phi epsilon. Let me recall you that phi epsilon are good functions, yeah? They're bounded and so on. So we just require this one. And it occurs that uniform finite absolute continuity leads to the weak compactness of the family of considered family. So let me give you two theorems which prove this statement. Consider Hilbert space H instead of B. Suppose that mu has finite second moment, and the family phi epsilon is uniformly finitely absolute continuous with respect to mu. Then the measures phi epsilon mu are weakly compact. Idea of proof is to control uniformly the rest of the series of such kind, where EK is some orthonormal basis. Maybe you remember that actually the uniform convergence with respect to epsilon of such series is a condition of the compactness in the Hilbert space. So how we can control it? You see here second moment, so we can control it through the fourth moment with respect to measure mu, but we already discussed that if measure mu is polynomial non-degenerate, this fourth moment can be controlled through second moment of measure mu, and for measure mu, such series converge. Yeah. Next case, consider now Banach space C01 theorem. Suppose that mu is again polynomial non-degenerate and satisfies the following condition. Oh, excuse me, here must be alpha. I just here is alpha. Here is if phi epsilon is uniformly absolutely continuous with respect to mu, then the measures phi epsilon mu are weakly compact. Let me comment the condition of the theorem. You see that it looks like Kolmogorov condition, but everybody remembers that in Kolmogorov condition we have to use T2 minus T1 in power which is greater than 1, strictly greater than 1. But again, it is not necessary now because mu is polynomially non-degenerate. Then, as I said, we can control uniformly force moment and arbitrary moment like 100 moment and so on through the second one. Due to this, we have situation exactly like in Gaussian case. Let me call that in Gaussian case, Hölder continuity in L2 sense gives existence of continuous modification. So we don't need in this case alpha to be greater than 1. And if phi epsilon is uniformly finitely absolutely continuous, then these measures phi epsilon mu are weakly compact. Again, idea is to check Kolmogorov condition, because as we remember, Kolmogorov condition, which holds uniformly for the family of measures, is sufficient condition for these measures in 0, 1 to be weakly compact. Of course, we have to control the value at least in some point, but it also follows from a finite absolute continuity. So you see that the notion of finite absolute continuity, uniform absolute continuity, is very useful when we have when we work with finite with polynomial non-degenerate measures. Now let me give you application of previous formal considerations. Consider the following example. Suppose that we have a centered Gaussian process such that it satisfies. Oh, excuse me again. I miss here two. Which is Hölder in a sense of convergence in square mean. And of course, in this sense, it has continuous modification. Suppose that minima of its variance is greater than 0. So then the result is surprising. Then the local time exists as a positive generalized function. Why I am saying that result is surprising? You remember a lot of different cases when we have existence of the local time for Gaussian processes. Brownian motion field, fractional Brownian motion, but for special Hertz parameter, like it is greater than 1/2, or some say for it depends for one, it depends on definition of fractional Brownian motion. Secondly, we have the prominent paper of Horowitz with somebody, where they created this notion of local non-determinism. And it is sufficient condition for Gaussian process to have the local time. But here, let me emphasize, this local time exists as positive generalized function with respect to distribution of p eta of eta itself. Let me recall you the situation with Brownian bridge for Wiener process and with delta measure concentrated on the function equal to 0 for another process. The same functional. The same happens there. I don't discuss existence of the L2 limit. I don't discuss the existence of this local time in the space of Wiener functionals. If we have some representation of eta, like in fractional Brownian motion, we have the integral representation of the fractional Brownian motion, like some integral with respect to W with ugly kernel, which blow up in some near diagonal. Yeah. So I don't ask for this. I am asking for existence of such generalized functional in a sense of chaotic expansion with respect to eta. Again, the chaotic expansion does not consist of multiple integrals with respect to eta. Eta can be non-semi-martingale and very ugly process. We just insist eta is Gaussian, so P distribution of eta is Gaussian measure. So with respect to this measure, we can do anything. This is the first result. Second, let's consider the integrator in RD generated by the invertible operator A. Let me recall the definition of integrator. It is very simple. Just take invertible operator A in the space L201. Now let us consider the process eta, which is for every value of parameter t, the integral from 0 to 1, and under integrals with respect to w, we have a function a applied to the indicator of 0 t. Then we just have such a process. They have nice properties, and we discuss these properties a lot at this seminar. But you see, there exists generalized local time for this integral. Generalized local time. It does not depend on dimension. Just take u, which is not equal to 0. Again, this generalized local time is an essence of distribution of eta itself. And the measure which is corresponding to it can change drastically if we take another integrator. There exists local time of self-intersection. And I must say that these two results are rather technical because we need some estimations to ensure that we have the limits and the limits of kernel, and to ensure that we have a uniform finite absolute continuity. But it can be done, and the paper is already submitted. You can find it in arXiv. That's all what I wanted to say. Thank you for attention. But before questions, I want to show you the references. There is a huge list of references, so I did not. I did not. Oh, okay. Sorry. Now let me do this as follows. So let me open it again. I was I am expecting that it will. Okay, but okay, no problem. Oh, okay. Here is the list of the reference. Let me tell you something about this list. You see here the book of Adler and Taylor, Random Fields and Geometry, and this is one of the most well-known and most good reference about different geometric aspects of random fields. We use it when discuss these self-intersections and Rice formula, because as I said, Rice formula related to crossings can be obtained very easy by formal calculations with different functions. Second and third book, Billingsley and Array Engineer, are very nice reference about the properties of probability measures on Banach space, absolute continuity, density, weak compactness, and so on. So 4 and 5 are devoted to polynomial measure and to polynomial, excuse me, self-intersection measure, and to consideration of intersection local time as a white noise function. Here is references of me and Izumtseva, Ryabov, Salhi, devoted to different aspects of generalized local times. And here you see the references about the, again, self-intersection local measure. But also, it is good to see the paper of Kuh, don't care data function as generalized Brownian function and its application. He has several papers, and unfortunately, we don't actually we don't put here another paper of Kuh in Acta Mathematica. I think like 1984, where he has a good idea to define the exponent from different function, yeah, as a generalized function. Hollander again, random polymer. Katz, this is well-known reference for these formal calculations. Legol again about the multiple self-intersection. Very good reference is the book of Malliavin. because in book of Malliavin you can find, at least in Gaussian case, the notion of Gaussian capacity and the property of measures concentrated on the set of positive capacity. I must say that Georgy Ryabov defended his PhD thesis on the subject of finite absolute continuity, so you can see his paper on this subject. Rosen again did a lot in the space of in the subject of self-intersection. Simon wrote a very nice presentation, I think, of white noise theory from the very beginning, and you can find a lot in his book. And finally, the paper of Sugita, where he produced his measures corresponding to generalized function. That's all. Thank you for attention, and maybe somebody have questions or comments, please.
Yes, I had a question about last two results of you.
Okay.
You have a process eta.
Yes, here is it.
I understand correctly that this is a Gaussian process.
Exactly. Yeah, exactly. Of course, I understood. I understand that it result is very surprising. But let me recall you, this is not.
Eta is a Gaussian process whose distribution is finitely absolutely continuous.
No. It is simply Gaussian process. Then the family which approximate local time is finitely, uniformly, finitely, absolutely continuous with respect to distribution of eta. It must be proved, but it was proved. And then we get the result that the local time exists as a positive generalized functional with respect to distribution of eta. This is very important.
So, in principle, eta can be concentrated on the set of zero capacity with respect to mu.
No. We forget about Wiener measure at all.
Okay.
There are no Wiener measure.
Okay.
Eta has its own. For example, eta can be like take some function like 1 plus t squared. This is the function. Multiply it by standard Gaussian variable. You have an example of eta. Take arbitrary Gaussian process which has Goelter property in square mean and non-degenerate variables.
What you prove the distribution of eta has no relation to the Wiener measure at all.
I even in this example even don't mention Wiener measure at all. Yeah. This is a very important difference. We don't say that eta has local time in the usual sense. Even generalized local time in the sense of Wiener functionals. It has a generalized local time in the sense of eta function.
Eta functional, yes.
Yes. Yeah. Exactly.
Okay.
This is a very important thing in our construction because actually here Gaussianity is not so important. You can put there instead of Gaussian, you can put there any process which has polynomial non-degenerate distribution and satisfies this condition, Goelter condition. Then it has generalized local time. For example, it can be now, you can imagine a Wiener process which is shrinked on the ball. So it means that Wiener process conditioning to be in a tube -1,1 has local time. Yeah.
Thank you.
Okay. Maybe some other questions.
I have one question.
Okay.
Is it possible to find out the distribution of such a local time?
I think yes. I think yes, because you remember, it has a chaotic representation. What does it mean? That we know the integrals of this measure. This local time is a measure on the space C01. And we know integrals from this with respect to this measure of finite dimensional polynomials. So we know all moments of this measure. So one can create a characteristic function, and one can create something. By the way, our previous paper with Naoufel was exactly devoted to this question, but in case of Wiener measure. We considered generalized functional related to the self-intersection for Wiener process in high dimensional and high dimensions, and we proved that this measure has satisfy large deviations principle. Of course, we can say a lot about obtained measure.
Okay, thank you.
You're welcome. Maybe other questions? Okay, if there are no questions, thank you for your attention again. And maybe Georgi know who will be the next speaker.
Next speaker will be Mykola Ivanovich Portenko.
Or so we will expect Nikolai Ivanovich your talk. For today we finish our work. Bye everybody.
Thank you, bye.
Thank you. Bye.